test till Tuesday. Sound good?
Yep.
Tuesday? Awesome. Monday will be a review day. Awesome. We lost a day. I thought there were gonna be storms tonight, but I don't see anything. Are they coming?
That's what
Did
it
they
is.
die out? Did they die out?
It's supposed to be at 8 o'clock.
Are they heavy or just rain?
Weather.com says it had a thunderstorm, but it doesn't really say that much.
Okay. Hey, thanks. Everyone, so, we've done 3 optimization problems. So we did one. We had a box, right?
Mhm.
All right, we took the box, it was flat. We maximized volume. We had a parabola. We had to find the maximum area inside the parabola, right? Described inside of it. And then we distanced to a ellipse from one point, and we found the point that would be furthest away from the point that's sitting on the ellipse. Cool. What's neat about that, and you relate it to real life, is like, you know, the Earth going around the sun, it's not a perfect circle, is it? It's an ellipse. But sometimes we're closer, sometimes we're what? Further away and stuff like that. It's the same thing. Find the one day what's the furthest away, closest. That's what's kind of neat. How about, we didn't do one like 15 now. Did anybody get a chance to do 15?
I tried.
Let's do it. Okay, that's a good one. We'll start with that one. We didn't want, you know, 12, I was looking at the, you know, handpicked, I want some really good ones from 4-7. Handpicked some good ones, but let's look at 15. This is from the textbook on page 332. Let's check this one out. All right, optimization. What do we got optimized? If 1,200 centimeters squared of material, all right. All right. That's area, right?
Mhm.
Yeah, squared. Is available to make a box with a square base and an open top. Find the largest volume of the box. So we got 1,200 centimeters squared of material. We're gonna make a box with a square base and open top. Find the largest possible volume of the box. So let me just go over here and say, what are we trying to maximize or minimize? Volume. Alright, so that's what we're trying to what? Optimize. We're trying to maximize volume. What's volume of a box?
Length times width times height.
Alright, let's start with that. Eventually we'll have to get one variable, right? We'll get B in terms of like X somehow. But all they gave us was the material. And it's got 1,200 centimeters squared. It's gonna have a square base and an open top. That's all we got. So in material. We're gonna open top, so let me write that down so everyone's okay with that. Square base. Open top. Well, good, I'm glad it's a square base. So if I call this length X, that length is also what? X. So far, so good? Okay, so at least I can call the square base X by X, but then we don't know if the height's gonna have X, right? What do you wanna call the height? Y?
Mhm.
You wanna go with that?
Yeah.
All right. I just wanna call it H. I'll call it Y. Now, material. Isn't that all the sides added up in terms of their areas?
Mhm.
Let's start out. We've got 5 sides to talk about. You've got these 2 sides, you've got these 2 sides, and then you got the bottom. Right? All right, let's start with the bottom material, which is 1,200.
Is y the height?
Yeah.
Oh,
If you want to call it H, we could. I just figured we'll call it Y. At least the base has an X by X, right? But now the material, we gotta add up all the areas of all these sides, right? We got a bottom and then 4 sides are on this, right?
Mhm.
Open top, so nothing on the top. Let's start with the bottom. What's the area of the bottom?
X squared.
Okay. We know that's what we're trying to maximize, but we gotta start with this thing, right?
Mm-hmm.
Alright, x squared plus, alright, let me shade this side. What would be the area of that side?
XY.
XY. Alright, we got two sides taken care of, we got three sides left. True? What would be the area of this side?
XY.
Another XY, alright. You can put two XY, I'll just write it out. There's side three. There's two more sides. What's this side? XY.
Right.
And finally, what's the other side?
Same XY.
Alright. What's XY plus XY plus XY plus XY? We get four XYs, huh?
Mm-hmm.
Cool. Could be the hardest part to the problem. Right there. Just the idea, we gotta think about what does material mean. Like material, well, that's the area of these sides. And we gotta add them all up, right?
Mm-hmm.
That could be the hardest part to this problem. So now we have that, we'll return to this. We know we can't differentiate until we get it in terms of one variable. Well, at least I know we can call the length x, we can call the width x. We don't have one variable.
We can solve for y in the equation.
There we go. I would agree. Like, our goal is to just get all in terms of one letter, one variable, and you said go over here and solve for what letter?
Y.
Would agree? And then we'll roll. So I really think this is probably the hardest part. This idea, you go, what do I do with it? And we had to think, well, material is just all the areas added up. There's an open top. We had to just make up letters and put letters down. And we said, well, we can call these x's because it's square, but we'll just have to call that a different letter. All right, now we got to solve for y though. Subtract x squared. All right. And then what's y equal to?
1200 minus x squared by 4.
All right.
By 4x, sorry.
1200 minus x squared divided by 4x.
Mm-hmm.
I'll put a circle around it. And where are we inserting u? Swing around here. Oh yeah. Now we got it. X times an x. Of course that's x squared, but I'll keep it like that. And then you got this 1200 minus x squared all over. Let's simplify that.
You can take one x out. The
Let's
4.
do that. We're going. So far, so good, Amber, right? On all this? I think that was the hardest part, just kind of coming up with that stuff. We solved for y, so we can insert it there, and now we got all one variable. And when this is number 15. It's on that page. All right, now, what's v equal to?
1200x minus x cubed over 4.
Is everyone okay if I write these as two separate parts? Cool. So what's 1200 over 4? Alright. And then I get this lonely x cubed over 4. But everyone's getting that?
Mm-hmm.
I just don't want to do, you know, like a quotient rule or something. Or you could have done the 1/4 in front, but I just like this. Now we do what? Do I set this equal to 0 or do I differentiate then set it?
Differentiate.
Differentiate, right?
Mm-hmm.
Take the derivative, we'll set it equal to 0, all right. What's that derivative?
300 minus.
Remember, we don't need
6
quotient rule here, that's a constant.
3x squared over 4.
3x squared over 4. 3x squared over 4, when that 4 underneath there, it's like a constant, like a 1/4 in front, right? Is that it, level?
Mm-hmm.
Right. And we set this equal to,
0.
and then, Josephine, we just gotta solve that, huh? Go ahead, go right ahead. I'll play with the algebra. 3x squared over 4 equals 300. I don't want to do quadratic formula. How do I get that 4 and 3 off that side?
Multiply 4 thirds on the other side.
All right. Let's multiply 4/3 on both sides.
or minus, but everyone, are we gonna have to chuck the negative?
No.
Plus,
We're gonna
Just
chuck the
leave it
negative, don't we?
close.
Because this is
It's-
the length of
It's
somewhat.
maximizing.
It's some side, right?
Mhm.
So we got no negative in this answer. So we're getting, once again, and you probably noticed this with all these optimization problems, we keep getting this one lonely answer. We don't even have to do like a first derivative test. We're like, that's gonna be the answer. What's the square root of 400?
20.
Neat answer. Thanks, Stuart. Always comes up with these neat ones, right? All right, x is 20. Now we can wrap this thing up. You're at 20. You're 20. How do I get y?
1200 minus 20 squared over 4 times 20.
Oh, I'm looking around for it. Is that it right there?
Mm-hmm.
I was looking around, like, where's our y equation? Sometimes you gotta go back, Amber, and look in your notes, you know, like, up in the page where you started this thing, and you go, oh, there it
You
is.
just plug in 20 and then you.
It'll
write
just
your
plug
y.
in 20. Yeah, try it. It's probably gonna be a neat number too.
10.
There's a lot of symmetry with optimization. There's a lot of symmetry. 20, 20, and then this other number is,
It becomes 10.
yeah, it's interesting. 1200 minus 20 squared all over 4 times 20.
No. 1200 minus 20 squared is
We get
800.
800 over 80, which is what?
10.
That's the total.
Oh, okay.
Check that, Amber. We get 800 over 80, which is just a nice, neat what?
10.
10.
And so what are the dimensions? It's 20 by 20,
4,000
By 10
centimeters
bucks.
cubed.
right? And what were the units? They were all what?
Centimeter cube.
But it's neat. Like 10 is exactly half of 20, isn't it? You get a lot of symmetry when you're optimizing things. Same thing. I mean, calculus 3. Wait till you do it. You do the optimization there, you get a lot of symmetry. Do all this stuff. Do this, and you'll go. In the end, you'll go. Make it a cube. But if they take like a top off, that's what happens. It's not 20, 20, 20, and you go, it's 20, 20, 10. Right? I mean, you better run, do this problem with a top. You go, what happens? It becomes this nice cube. That's why, everyone, when you go to these, you ever ship things, UPS stores and all that? You go, yeah, I need to ship this to Canada or whatever. They're like, well, what cube do you want? You want a 10 by 10 cube? Or they just call them, do you want a 10 cube, 12 cube, 14 cube?
No, there's a 10
It's
by
the units,
10. They
you
don't
know?
use them. They just use the
And they
area.
have all these cubes on the wall. They just
Uh-huh.
put them together. Why are they doing cubes? Because of maximum space and all that. I know. Hey, great job with this. Hey, any others in this section? I saw another one that was distance, and that I assigned was number 19. And we should do it. We should do it because this gives us extra practice with that distance formula. Do you remember it?
Mhm.
Yeah. Square root x squared.
And then plus, awesome. When you take calc 3, what will get added here?
Plus C.
Z2 minus Z1 squared, you got it. You'll love that stuff. Now what happens in this section in calc 3? 2 things. One section, your goal is to get everything in 2 variables. That's what you end up doing. But there's another section where this guy, this mathematician, came up with some neat stuff, where there's an easier way to maximize things. So it's just, I just think you all will love calc 3. You have to research that or Lagrange. They're called Lagrange multipliers. And use Lagrange multipliers to maximize things in multivariable calculus. Pretty cool. This method still works with 2 variables. You do it 2 variables and then you go, I'll try Lagrange multipliers. And sometimes the algebra is a little easier in Lagrange multipliers, but not always. I want to point that out. Because you end up just solving systems of equations with day. Just systems of equations, which you all have experience with. You got two equations with two variables, and you gotta do like a substitution. Kinda like this stuff. Just like this. Alright, everyone. This is number 19. Could you find, unless you want me to change the line. Does anybody want me to change the line so you can practice it? What do you all think? Just do it? I like it. Alright, I'm gonna just do it. To find a point on the line, y equals 2x plus 3 that is closest to the origin. Well, maybe we should just start with an image, just to get an idea what's going on. Number 19. And I'll reread it to you, Josephine. We gotta find the point on the line, y equal to 2x plus 3, that is closest to the origin. Now, they never said this word. Josephine, they never mentioned it. But guess what we need to use in this problem when we optimize? The distance formula. We're gonna have to use this distance formula. Because it deals with distance, doesn't it?
Mm-hmm.
Find the point on the line, y equals 2x plus 3, that is closest to the origin. I think it always helps when you and I just get a sense of the problem. They never said we had to sketch an image, but pictures help us see things. Here's the origin. Now 2x plus 3, rise over run and all that stuff. What's the y-intercept? Alright, it's going through here. Rise 2, run 1. Does that work? Okay. There it goes. Did you get a feel for where the answer's